Flight director to all stations. Let's get a final check. Systems are green, telemetry is locked, and we are absolutely clear for pre-flight calibration. Welcome, candidates. Welcome to this rigorous pre-flight explainer briefing for Cambridge Mathematics 9709. Specifically, we're targeting Mission 3.8 today, differential equations, focusing on separating variables. Now, I need you to step into the role of the pilot today. Seriously, get into that mindset. Because here in this command center, we treat your Cambridge syllabi like critical flight launch protocols. There is zero margin for error when you're navigating the upper stratosphere of AS and A-level mathematics, right? I'm your flight director, and my singular job today is to ensure your analytical frameworks are completely stabilized before you are cleared to launch into your actual exam paper. We're going to look closely at the data, the direct examiner telemetry, and the exact structural pathways you need to take to secure maximum mark yield. So strap in, check your vital gauges, and let's initiate the countdown sequence. Okay, let's dive into this, because this number right here, flashing on your main dashboard, is the exact reason we are running today's simulation. 15. This specific syllabus topic, differential equations by separating variables, it carries a massive, massive payload. It accounts for approximately 15% of your total examination marks in this paper. Now, I want you to think of this 15% as your main booster stage. If you miscalculate your fuel burn here, or if your structural integrity fails on this specific question type, you simply will not have the propulsion required to reach that A-star orbit. It really is that critical. We aren't just looking at a minor course correction today. We are looking at a foundational pillar of your entire mathematical flight plan. Listen, the examiners know this is where the pressure peaks. They specifically design these questions to test if your cognitive systems can handle the G-force of high-level calculus. So we're going to engineer an absolutely unshakable response model to ensure you capture every single one of those percentage points. We are not leaving any fuel on the table. To guarantee mission success, here is our official mission protocol. First up, core concept calibration. Second, we'll map out the launch sequence methodology. Third is hazard avoidance, spotting the traps. And finally, our post-launch debrief. Let's get right into it. Phase 1, core concept calibration. Let's align our sensors. Before we even think about touching a formula, we need to understand the actual airspace we're flying into. Official Cambridge assessment objectives target 3 distinct layers, okay? First is knowledge, your basic algebraic rules. Second is application, what happens when variables start shifting around. And third is analysis. That's the exosphere. And this brilliantly illustrates the difference between your standard average candidates and our top scoring commanders. Let's run a quick simulation with 2 theoretical pilots on our telemetry screens, Pilot Alex and Pilot Sam. Look at Pilot Alex. Alex initiates a low-altitude trajectory. He relies purely on superficial breath and basic recall. When he hits a complex differential equation, what does he do? He just dumps raw integration formulas onto the page without properly separating the x and y variables across the equal sign first. It's a mess. He burns all his fuel, overloads the system, and never breaks the atmospheric limit. Now look over at Pilot Sam's telemetry. Sam steers incredibly fast. She executes a rapid integration sequence, but here's the fatal flaw. Sam ignores the structural boundary coordinates. She completely misses the command words, totally forgetting to apply the initial conditions to find C, that crucial constant of integration. What we actually need from you is the high propulsion evaluative launch. This requires systematic analysis. It means actively questioning your assumptions, considering the exact constraints of the variables, and providing hard evidence-based reasoning for every single line of working. You don't just calculate, you command the variables to separate logically. Phase 2, launch sequence methodology. Time to build the engine. Let's move to the main console and see how this builds your ultimate fail-safe mechanism. We are shifting from theoretical physics straight into the core engineering of problem solving. A successful flight requires logical, structured reasoning over just raw memorization. Look, differential equations are highly volatile. If you try to integrate before you have strictly grouped all your y terms with dy on one side and all your x terms with dx on the exact opposite side, your system will instantly overload. It's an automatic fail. So every single time you face a 3.8 differential equation, I need you to execute this strict 5-step sequence. Step 1. Deconstruct the question, identify the given differential equation, and highlight the boundary conditions. Step 2. Extract relevant data. Ask yourself, is this a direct, pure math problem, or is it disguised in a real-world context, like chemical reaction rates or population growth? Step 3. Select your analytical framework. This is the physical separation part. You use your algebra to physically move every y function over to the y side and every x function to the x side. Step 4. Execute with clear notation. Now you integrate both sides simultaneously. And crucially, literally do not forget this, add your constant of integration, plus C. That is your locking pin. Step 5, verify your results and present them with the correct terminology. You use your extracted boundary data to solve for C and then resubstitute it back in to find the particular solution. Boom, clean orbit. Launch trajectory hold. Before we deploy this top-band framework to clear orbit, we need to optimize your educational flight deck. Take a second right now to subscribe to Ace the Exams, that's at Ace the Exams, and enable all notifications so you never miss our weekly flight-tested exam hacks, whether you are launching at IGCSE, O-levels, AS, or A-levels. Okay, trajectory resuming. Now, what happens if we encounter an unexpected structural data loss mid-calculation? What if you accidentally drop a negative sign in step 4, threatening a complete mission termination? This is exactly where we deploy our backup thrusters, the method mark strategy. The entire Cambridge assessment framework relies heavily on this. The method mark strategy is a procedural fail-safe mechanism. It's where examiners award you marks simply for demonstrating the correct analytical process and showing clear logical working regardless of a minor arithmetic glitch. It is the examiner's way of rewarding your logical reasoning and your systematic analysis, even if your final number is slightly off. But listen to me very carefully. These fail-safe thrusters only ignite if, and only if your working is entirely visible on the radar. If you do the physical separation of variables purely in your head, or punch the integration straight into a mental scratch pad without logging it on the physical paper, the examiner cannot see your telemetry. And if there's no telemetry, there are no method marks. You drop like a stone. I want you to treat this slide as an urgent Priority 1 incoming transmission directly from Cambridge Command. The Principal Examiner Report explicitly states, and I quote, "Students lose marks by not showing working. Even if your final answer is wrong, method marks can save you." End quote. Look, this proves that showing your systematic work isn't just a polite suggestion from your math teacher. It is a critical survival protocol. Think back to Pilot Sam. When Sam rushes through the navigation and makes a tiny addition error at the very end of the page, she doesn't crash the whole ship. No, she only loses the final accuracy mark. She still secures 80 to 90% of the payload purely because her sequence was structured, it was logged, and it was verifiable by command. In the high-stakes environment of 9709 mathematics, your ink on the paper is your black box recorder, literally. Do not leave the examiner guessing how you arrived at your destination. Make them see the logic stream. Phase 3. Hazard avoidance. Let's do a sweep for critical errors. I'm handing the controls over to you right now for a live radar sweep. We are currently analyzing the most common atmospheric anomalies that cause candidates to drop multiple marking bands. This is direct, raw telemetry pulled straight from the principal examiner reports. Now, what's really interesting about this slide is how easily these top 3 navigational errors can be bypassed if you are just paying attention to the HUD. Anomaly 1. Examiners report candidates confusing cause and effect. In separating variables, this often means setting up the differential equation completely backwards when you're translating it from a word problem or integrating with respect to the wrong variable entirely. Anomaly 2. Forgetting to check format and presentation. Okay, so you solved the equation, great, but did the question ask for y in terms of x? If you leave your final answer as the natural log of y equals some expression of x, and you fail to exponentiate both sides to actually isolate that y, you lose the final presentation marks. You did the hard part and fumbled at the goal line. Anomaly 3. Answers are not specific to the given context. This is a big one. If t represents time in seconds and your mathematical model spits out a negative time value, you must use evidence-based reasoning to consciously reject the negative value based on the context of the real world. Time doesn't go backwards. So lock this into your internal memory banks. I want you to create a custom mnemonic sequence right now, using the first letters of these key terms: cause, format, context, CFC. Calibrate flight coordinates, CFC. Every single time you finish a differential equation, run the CFC check. Did I map the cause correctly? Is my format exactly what was requested? Does my final answer survive the reality check of the context? Final phase. Phase 4. Post-launch debrief. Let's summarize the mission. At the end of the day, mastering this 15% payload is not about brute-forcing calculus. It's just not. It requires strict procedural sequences. You have to identify, extract, separate, integrate, and verify. It demands methodical, clear, line-by-line working to activate those life-saving method marks we talked about, and it requires a final CFC radar sweep to ensure your answers are formatted correctly and perfectly aligned with the real-world context provided by the examiners. You are now equipped with the technical methodology to not just barely survive Topic 3.8, but to absolutely dominate it. So flight crew, I leave you with this final system diagnostic. Have you calibrated your analytical frameworks to guarantee those vital method marks on your next launch? Seriously? Ask yourself, Are you going to be Pilot Alex, burning out on raw, unstructured memorization? Or are you ready to execute a flawlessly structured top-band evaluative launch? To keep your systems constantly upgraded, hit that subscribe button for @ASD Exams, click the notification bell right now to lock in your weekly masterclasses, and before you close this feed, drop a comment below sharing exactly which Cambridge subject and level, whether it's IGCSE, O-Level, AS, or A-Level, you are preparing to conquer next. Flight Director signing off. I will see you in the next simulation. Keep your coordinates locked and keep your working clear.